For this lecture, we're going to be talking about additional circuit analysis techniques for you to be able to solve or analyze circuits faster and easier, actually. And there are two kinds, or there are two algorithms or ways to solve a circuit much better than identifying a KVL loop or KCL node. And these are your nodal and mesh analysis. Okay? So, for example, if we consider a power system, what shall we do if we want to know the power consumed by each house? Then we have to do the Thevenin, basically the Thevenin's theorem for each house. In a lot of houses there. No, that's a little that cannot be done even if you brute force the data on a computer. Okay, so using nodal and mesh analysis, we create a systematic way of analyzing circuits. And network reduction is not needed for that. Both methods produces n equations and n unknowns, and unknown quantities are actually solved simultaneously on both methods. So first, let's look at a nodal analysis. These are the steps to solve a circuit using nodal analysis. Okay, so you have 7 steps. I excuse me. First, you label the nodes in each in the circuit. So label each nodes. Prefer to label them with letters. Okay. So from your labeled nodes, you create a reference. Okay. So we call it the grounded node. So this works actually because we're looking at the potential, the voltage potential. Sorry, not that's a weird term. The potential at each node. Okay, and if we assume one to be a reference node, the potential difference between two nodes are not changed. So think of it as something like if you have some level here with a height h1, okay, and some ground level, of course, with a height 0, and another level with a height h2. So between these heights, there is, for a mechanical system at least, there is some change in gravitational potential energy in these heights. So if we assume that this is 0, then this becomes negative h1, and this becomes negative h1 plus h2, or h2 minus h1. The change in energy, however, between the two heights is remains constant. Okay, so you can set any height here to be 0, but the change in energy between those heights are not does not change. So when solving for voltages in a circuit, you're looking at the potential difference between two nodes. So it doesn't matter where you define the ground node, you'll still get the same voltage difference between each element in your circuit. Okay? So define then a voltage rise of variable for each node. Let's put an asterisk there. So these are nodes other than the reference node. With respect to the reference node, by inspection, determine the values of some voltages that will be evident later. For every node, the unknown voltage, there's an unknown voltage rise. You create a KCL equation, and the current should be written in terms of the voltage rise variables. And you solve the system equations and find the required quantities from the circuit. Okay, so for example, we have this circuit right here. It's a simple circuit. Okay, so if we're gonna do KVL and KCL on this circuit, you need to set, so the method is you need to set a current for all the resistances, and you need 4 equations from your KCL and KVL. But that's not what we're gonna do in this in this example. So we'll do nodal analysis. First is you identify the nodes. So these are the nodes. This is node A, node B, and node C right here. Here you go. So node A, node B, and node C are these. Okay. And this is another node right here at the bottom. Okay. So this is called, let's call it node VD. Okay. For consistency. But we set it now to 0 volts. So we call this the reference node or the ground node, or the node at which you have a 0 potential. All right. So, okay. Oh, sorry. Where was I? Oh, here we go. Alright, so now we need to find the voltages VA, VB, and VC using nodal analysis. Alright, so first things first, you identify this as a supernode. So why do we need to identify a supernode? There is current flowing through this voltage source right here. However, we cannot explicitly define that current since this voltage source allows any current to pass through it, unlike a resistor whose current is directly related to the voltage difference between the two nodes where it is connected and its resistance. For a voltage source, we don't know that. So then we just basically try to ignore it by defining this as one big supernode. Okay, so since there's a voltage source between two nodes that are not grounded, so take note, it's not grounded. So this, since there is a voltage source, we can't immediately get an expression for the current that is passing through it. Therefore, we need to just ignore it. Okay, so actually, the logic for that is just we create a KCL equation here, and let's say the current goes through like this. Let's call it some current I. Okay. So if we do a KCL equation using B, there is a current going through this resistor. Let's assume it's going this way. Then this current is the voltage across this resistor right here. And since this is the direction of the current, this is plus minus. The current that is flowing from this node to this node is VB minus VA divided by 6. And that is actually, well, this equation right here, but it's just a different direction. Okay, so let's try to write it down using Word. Okay. So the equation for this node B, okay, is VB minus VA all over, oops, okay, let's do that again. Okay, that's VB over VA minus VA divided by 6. And then there's the current that's flowing through here. So let's assume that the current is flowing out of the node. And since this is your current, it has a something like this. Okay, so it's flowing out of the node B. You get VB minus 0 over 3. That's the current that is passing through this resistor. Again, this is the voltage difference between on the resistor, which is defined by the potential here minus the potential here, which we set at reference. So it would be 0. So that's VB minus 0 divided by 3. So VB minus 0 divided by 3. Whoops. There you go. And finally, there's some current that is going through this voltage. Let's call it I. Then that's just plus I equals 0. Okay. Oops. Okay. So now we are going to look at the node here at C. Assume again that the currents are flowing out this way for resistors at least. So there's current flowing out here and current flowing out here. Okay. So for this resistor, The potential difference on the resistor here is Vc minus 0 divided by 4. So it's just Vc over 4. Sorry, that should be small c. And this is Vc minus Va. So since this is the direction of the current, the potential difference is something like this. So it's Vc minus Va over 8. Sorry. So that's plus Vc minus Va over 8. Oh wait, should be consistent. This is small c. And you have a current going in, so that's minus 5. The current going in, which is I, that's minus I equals 0. Excuse me. So now if we add these two equations right here, we'll get this resulting equation. So if we add these two equations, this I cancels each other out. And we just add the remaining terms right here equal to 0. This is the equation at your supernode B. So this is now your, supernode BC. So that is the logic on using nodal analysis in this example. Okay. So that's for supernode. It's not yet shown here. I'll show you later. So I actually forgot node A. So let's look at that first. Again, we try to assume that the currents are flowing out of the node here, and you have a 6 ohm resistor here. Therefore, the current flowing out is VA minus VB over 6. That is the current going through here. The current going through here in this 8 ohm resistor is VA minus VC divided by 8, and that is equal to 3 because the 3 is going inside the node. So it's going towards or going in the node. That is equal to the total current going out of the node. Okay. So this is your node A, and your supernode is this equation right here. So now we have 2 equations and 3 unknowns still. We need to define the third equation. If we look at this, supernode right here, this voltage source forces the voltage difference between VB and VC to 6 volts. Therefore, your third equation actually is this: VB minus VC is equal to 6, since the potential difference between these two nodes is forced to be 6 volts by the voltage source. So now we have 3 equations and 3 unknowns. We just need to simplify them. We get these 3 equations and we solve them simultaneously using your calculator. You'll get these values right here. Okay? Alright. So another example. Okay. So it looks like it looks like this actually, but instead of a voltage source, independent voltage source, we now have a dependent voltage source. Okay. So we change that into an independent voltage source. Since this is a voltage source, then we actually define this again to be a supernode. Alright? So it's actually that. So again, node A, assume all the currents are flowing out. Okay, but we don't mess with the current of this current source right here. So again, currents are flowing out. Then it becomes VA minus VB over 6, since again, this current defines polarity of the resistor like this. So the higher polarity is at VA, then the voltage difference is VA minus VB divided by the resistance. That's the current. And the same logic can be done through this, and we'll get the equation at node A. Likewise, we set up the equation for the supernode in this case. So the supernode is still the same. So if you don't actually understand what happens to a supernode, you can again repeat the calculation. You assume a current I that is crossing across the flowing through the voltage source, and when you add the 2 equations, you'll get the equation for the supernode. Okay. So that is this equation right here. So since we have a dependent voltage source, the dependent voltage source forces the potential difference between VC and VB to be equal to 2Vx. The positive sign is in the direction of VC. Therefore, the equation between them is VC minus VB is equal to 2 times Vx. But Vx is defined as this voltage right here. And this voltage has its positive side to VA and its negative side to VC. So therefore, Vx is equal to VA minus VC. So you just need to substitute that into this equation, and we now have the same three equations and three unknowns. So it's still the same difficulty level. Just input it to your calculator and you'll get this equation right here. Alright. So after nodal analysis, we now have mesh analysis. If nodal analysis deals with nodal voltages or nodal potentials, for mesh analysis, we are gonna deal with loops. And we assign a mesh current and that is flowing to each mesh in the circuit. So again, a mesh is the simplest loop in the circuit. It does not flow through any branch. So it's just a simple loop within the circuit. I'll show you again in an example. So you write a KVL equation for that loop, and we have an unknown current. Okay, so for every loop, I use numerical values to show the loop. You solve the system of equations and solve the required quantities in a mesh current for using the mesh currents. Okay, for example, in this circuit we have three meshes. So that's 1, 2, and then 3. So this wait, where is it? Okay, here we go. So this mesh right here, this loop right here is not a mesh since it crosses a branch like this. Okay? So there you go. So find the voltage Vx using mesh analysis. So the KVL equations for meshes 1 and 2 right here. There you go. This is mesh 1, mesh 3, mesh 2. So mesh 1, sorry. Mesh 1 is this equation right here. So the the KVL equation is this. So it passes through a 2-volt source and passes through this resistor and passes through this resistor. Okay. So we define a current in this loop to be I1. If it does not have, or it's not adjacent to another loop or another mesh, then the current flowing through this branch here, like this, is equal to I1. Okay? So what the logic in that is, it does not cross, or it's not adjacent to any branch, therefore it's not flowing, it's not adjacent to any branch, therefore the current is just defined in this manner right here. Unlike in these two, it's adjacent to a branch, therefore the value of the current through each of these elements changes. Okay? So, for example, if this is I1, quite simply because there's no adjacent branch next to this mesh right here. This is I1, then in this case, the current here is I2. Okay? So this is I1 and this is I2. Alright, and then we have the current flowing through here in the direction of I1. So since we're looking at this mesh, we assume that the current flow here is in the direction of the loop. Okay, and let's call that some current I. Okay, so if we do KVL in this loop, then we have, since the direction of the current is defined by the loop, this is the polarity of the voltage here. Then the voltage here is equal to some value V, which is equal to I1 times the current here. So let's type that. Okay, so this would be 16 I1 negative. Okay, since your loop is flowing from positive to negative, here also your loop is flowing from positive to negative, so that's minus 2. Here, since you assume the current I is in this direction it's in the direction of the loop, then we assume that the voltage here is plus minus. So you ignore this Vx first. Okay. So the polarity of the voltage here is plus minus. It's equal to 40 times I. So it's minus 40 times I. But what is the value of I? The value of I can be solved through KCL at this node. So the KCL at this node is equal to the sum of the currents going in, which is I and I2, equal to the current going out, which is I1 here. So by just transposing I2, we'll get that the current flowing through the 40 ohm resistor is I2 minus I1. Okay? So now we can substitute that here, and we'll get this expression for the loop or the mesh 1. Next is the mesh 2. Okay? The mesh 2, we assume that the current flow through each of the branches in the circuit is defined by the loop. Therefore, the current flow through the 40 ohm resistor is this, the current flow through the 20 ohm resistor is this, and the current flow through the 40 ohm resistor is this. Okay? So now we do KVL in these loops. So let's say this 40 ohm resistor has a current I40. There you go. And this resistor has a current I20. Right? So again, the direction of the current is defined by the direction of the loop. And we get the KVL equation that is defined by mesh 2 is equal to, so let's type that. So we start here. Since this is the flow of the current, then the polarity is something like this. Okay, the polarity is something like this. Then it's equal to 40 times, negative 40 times I40. Same is true with this resistor right here. That's minus 20 times I20. And this is a voltage rise from negative to positive, so that's plus 5 volts. And this is, again, the polarity is defined by the direction of the current, so that's plus minus. So that's minus 40. And the current flowing through this, since it's not adjacent to a to a another mesh, therefore the current here is actually just I2. So it becomes minus 40 times I2 equal to 0. And if you simplify both 1 and 2, you'll get these expressions right here. In mesh 3, in this case, so if you look at the mesh 3 right here, since this current source does not have an adjacent, oh wait, I'm forgetting something. Right! There's a current flowing through this 20 ohms, which is I20, as we assumed it earlier. And since this branch of the circuit does not have any adjacent branch, or adjacent mesh, sorry, then this current flowing through here is actually I2. In this case here, your 30 ohms, alright, has a current that is flowing through here, defined by I3, since it's not adjacent to any mesh, then this current right here is I3. Okay, so doing KCL at this node, I20 is actually equal to I2 minus I3. So we do KCL. So the sum of the currents going in is equal to the sum of the current going out, and we isolate I20. It's equal to I2 minus I3. There you go. So we substitute that in this expression right here. Same is true with the 40 ohms, and that is just I2 minus I1. And this is your second equation. You simplify that, you'll get this. Finally, we have I3. So since, again, there's no adjacent mesh here, and it's just a current source, then I3 is actually the current flowing through this branch already, and that is already 1 ampere. Therefore, I3, the mesh current I3 is actually 1 ampere. So you just need to substitute that here, and you only have two equations and two unknowns for this problem. Okay, so you can now simplify that. Solve for I1 and I2. You get these. And finally, we get the voltage Vx here. So remember, Vx is this. Therefore, the current flowing through Vx is this current right here, which is equal to I2 minus I1. So voltage is just defined by Ohm's law, and the voltage Vx is calculated as such, and you get 5.2 volts. All right. So given a choice, then what would you use? So it depends. All right. So there is a complexity in setting up the equation. It's subjective to people, and but the pro tip here is you choose the method that gives you less number of unknowns. Okay. So for nodal analysis, the number of unknowns is equal to the number of nodes minus 1. For mesh, it's the number of, well, basically the number of meshes. All right. So, okay, so every voltage source for the nodal connected to the reference node reduces the number of unknowns by 1. For every current source connected to the periphery, it reduces the number of unknowns by 1. So we have shown it here. You actually only have two unknowns, I1 and I2, since I3 is equal to this. It's dictated by this current source right here. Okay, so here we go. So for example, let's do nodal analysis in this circuit. Okay, so first we do nodal analysis. We have 1, 2, 3, 4, 5 nodes. Okay, so for node A, we have 3 ampere going in, and there are two resistors connected to it. Therefore, this would be VA minus 0 over 2. This is this term. VA minus VB over 4. This is this term. Okay? So you have for node A. For node B, assume that the currents are going the opposite way. Right? So going out, and you consider the current that is passing through this 100 ohm. You consider the current through this branch, and you consider the current through this branch. Alright? So we have what? So this is negative 4 since it's going away. You just transpose it. And so that's negative 4. And this current going from VB to VA is equal to VB minus VA over 4. Current go from across this 5 ohm resistor is VB minus 0 over 5. Current passing through the 6 ohm resistor is VB minus VC over 6. And finally, the current going through the 10 ohm resistor is VB minus VD over 10. Okay. For node C, we look at node C right here. That it has 3 components connected to it. So that's here, the current going in, and assume that the currents in the resistors are going out. Therefore, you have 4 is equal to VC minus VD over 8. This is here. And VC minus VB over 6. This is here. Node D, still the same, right here. So we have node D, and we have this current going out here, this current due to the current source, and this current going out here. So that's, since it's going out, it's negative 5. So this is going out, VD minus VB over 10, right here. And we have VD minus VC over 8. That's the current going through here, and you have this. So you now have 4 equations and 4 unknowns for this example, for nodal analysis. Now for mesh, so if you notice, So this one mesh, two meshes, three meshes, four meshes, five meshes. However, in this mesh right here, the current is already defined. Therefore, it's just 3 amperes. Also here, the current is already defined. Therefore, it's 5 amperes. We are now left with 1, 2, 3 meshes left for our mesh equations. So if you look at that, then let's set up the mesh equations. So first, mesh 1, it's this mesh. Alright, so this mesh, well, first you define that the direction of the currents across each resistor is the same as the direction of the loop. Okay, and something like that. Alright, so that's 2 ohms. It's adjacent to this mesh right here. Therefore, the current flowing through this 2 ohms is I1 minus 3. So that is equal to, so let's write that down here. So that is equal to 2 times I1 minus 3. And we have, since there is no adjacent mesh here, then it's just I1 that flows through this 4 ohm resistor. Therefore, that's just minus, since it's a voltage drop, minus 4 times I1. And finally, we have this 5 ohm resistor. It's adjacent to the 5 ampere branch. Therefore, the current flowing through the 5 ohm resistor is I1 minus 5. Therefore, it becomes minus 5 times I1 minus 5. There you go. And that is equal to 0. That's the equation for mesh 1. Ooh, there. For mesh 2, well, since we have a current source here, we can't immediately define this I2. For 1, this current source is adjacent to I3. Therefore, instead of just using mesh 2, same concept as your voltage source in the nodal analysis earlier, you create a super mesh. So, something like this mesh right here. You effectively avoid this 4 ampere current source by selecting this super mesh, as we call it, which is actually derived by doing the KVL of this loop plus the KVL of this loop. You'll get the KVL of this bigger loop right here. It's kind of the same derivation using the super nodes earlier. Okay, so now the let's focus on the KVL across this loop right here. Okay, so first we have this. Since the loop has this direction, so take note, the meshes should have the same direction. Okay, so since this is the direction of the loop, we set the direction of the current like this. The direction of the current here is like this, and the direction of the current here is like this. Therefore, since this is a voltage drop, it becomes negative 10 times I3, since it's not adjacent to any other meshes. So that's negative 10 times I3. Next is this resistor right here. Since it's adjacent to the 5 ampere mesh, then the current going through this 8 ohm resistor is I3 minus 5. Therefore, the voltage is I3, there you go, minus 5. And next, we have this. We have this 6 ohm resistor. It's adjacent to the 5 ampere loop. Therefore, the current flowing through the 6 ohm resistor is actually I2. It's I2 minus 5 amperes. So that's minus 6 times I2 minus 5 ampere equal to 0. Okay, so now you have 2 equations, but you have 3 unknowns. You now consider this mesh right here. So, sorry, not the mesh, the current source right here. So it's the same logic as your supernode. You can use this current source to define the currents I2 and I3. So let's look at that. All right. So in this node right here, in this node, it's covered by your mesh I3. Therefore, the current going through this node is equal to I3. Okay. Next is this current. So it's this current. right here, that is equal to 4 amperes, right? So the current going through here is 4 amperes. Sorry. Yeah, 4 amperes. There you go. All right. So now the current going through this branch, wait, we chose the wrong node. So erase all that. Um, we chose the wrong node. Sorry about that. Okay. So let's look at this node right here. It's much easier than here. This node actually has 1, 2, 3, 4 connections. This node has 3 connections. So at least it'll make the analysis easier. So this node, let's choose this one. There's a current going in 4 amperes. The current flowing through this resistor is I2 minus 5. The current flowing through this resistor is I3 minus 5. Okay, so we have 3 currents. It's I3 minus 5 plus 4. Okay, I3 minus 5 plus 4 equal to I2 minus 5 right here. So the minus 5 will cancel with each other, leaving you with this equation, and you transpose I3, and there you go. Your third equation is defined by the current source. The difference between the mesh current here and the mesh current here is actually 4 amperes. So to make it easier, not doing anything like this analysis, you can just think of I2 as the current with the same direction as I4 as the 4 amperes, and when I3 passes the 4 amperes, it has a different direction as the 4 amperes. Therefore, the 4 would be equal to positive the current that is with the direction of I4 of the 4 amperes, that's I2, and minus the current that is against the direction of the 4 amperes, which is I3. So that is the equation of your super mesh. All right. Okay. So uh, this is now your system of equations, and since it's only 3 equations and 3 unknowns as compared to your nodal analysis, which has 4 equations and 4 unknowns, it's actually easier to describe the circuit using your mesh currents. Okay. So to summarize, well, nodal and mesh analysis are actually useful methods of analyzing circuits, and it's better than using KVL and KCL, since, well, using KVL and KCL, you need to consider if the equations are actually independent of each other, and there are more unknowns than using nodal and mesh analysis. So it actually computes for unknown quantities based on what you're using. If you use nodal, you're using nodal potentials. If you're using mesh, you're using mesh currents. And you can simultaneously solve circuits without needing to simplify the entire thing. Okay? So no principle of equivalence. It's easier to solve, at least, and you can solve for unknown quantities simultaneously. So it's kind of like where it's asking for this value Vx, and then first we just ignore Vx, and then solve for the nodal potentials or the mesh currents. So given the choice to use nodal or mesh, um, the pro tip there is you use the method with less number of unknowns or equations. Okay, so that's the end of this lecture.